Hello Year 11, welcome to this third lesson in our Transition to AS Chemistry series. Do make sure you've watched videos 1 and 2 before starting this video so you are competent at calculating relative formula mass as well as calculating moles, because that will be essential moving forward. Also, do make sure that you download the periodic table because we will be using that quite frequently in this video. Okay. So our understanding of the term concentration, what does it really mean? Okay, well, chemists have to use concentration all the time because when you envisage the classic sort of stereotype of a chemist, they're stood there with solutions in front of them. Okay, so when we talk about concentration, we're talking about a solution, and fundamentally a solution is a liquid with something dissolved in it. Okay, now our concentration is typically always referred to as the amount of a substance, okay, amount of substance divided by whatever unit volume it's dissolved within. Okay, so amount of substance over volume. But depending on whether you've studied combined science or triple science, you'll have potentially different understandings of what we mean by this amount of substance and what we mean by this volume here. So I want to start off by talking about the most basic explanation of concentration, which is where we do concentration equals mass divided by volume. Now, the standard unit for mass that chemists use is grams. So we would need to convert any quantities that we are given into grams to begin with. And our standard unit for volume is cubic decimeters. So we need to understand, before we move on, this idea of cubic decimeters. Well, 1 cubic decimeter is the same as 1,000 centimeters cubed, or cubic centimeters. So if you were given a quantity in cubic centimeters, to get it into cubic decimeters, what you'd need to do is divide that by 1,000. If you had a volume in cubic decimeters and you wanted to convert it to cubic centimeters, you would need to multiply that by 1,000. So that conversion is absolutely essential if you're going to be calculating concentrations that have per cubic decimeter as its units. So let's do an example quickly. If you had 5 grams of a solid dissolved in 5,000 centimeters cubed, liquid, so we'll just say water. And we've got to calculate its concentration. Well, we've got a mass here. It's already in the gram format, so that's fine. But this volume here is not in cubic decimeters, so we're going to need to divide that by 1,000 to get it into cubic decimeters. So I'll do my sum in a different coloured pen. So our concentration equals mass, which is 5 grams, divided by that volume. So 5,000, just do this on the side here, 5,000 centimeters cubed divided by 1,000 to convert to decimeters gives me 5 cubic decimeters. That's 5 dm cubed. And therefore, 5 over 5 is 1, so we get a concentration of 1. But our units for this, well, we divided grams by cubic decimeters, so it'll be grams per cubic decimeter. So there's a really simple example of a calculation in grams per cubic decimeter. What I'm going to do is change the slide so it's got a bunch of practice problems where you've got to calculate in grams per cubic decimeter. You can pause the video and then come back to look at the solutions. Okay, so we've got 2 here. The first one, calculate the concentration in grams per cubic decimeter of a solution that contains 60 grams of a substance dissolved in 120 centimeters cubed of liquid. Second problem, calculate the concentration in grams per cubic decimeter of a solution that contains 1 kilogram of a substance dissolved in 50 cubic decimeters. And you can see here I've given you something in kilograms, so you have to remember a different conversion there. So pause the video and then we'll start working through the problems. Okay then, so the first one, we've got to remember that concentration equals mass divided by volume in this case, and because we're trying to work it out in grams per cubic decimeter, and we've got a mass, we've got 60 grams, so that's going to go on top, And we've got a volume here, but that volume is in centimetres cubed. So the first thing we're going to need to do is divide that by 1000, and that should give you 0.120 cubic decimeters. So we'll pop that there, and we'll do that sum in our calculators, and you should get an answer of 500 grams per cubic decimeter. Okay, again in our second problem we can use the same equation, concentration equals mass divided by volume, and I'll just call it vol for now, and we can see we've got 1 kilogram here, so there are 1000 grams per kilogram, so I'm going to multiply that by 1000 and you should get 1000 grams therefore. So we're going to have 1000 grams divided by 50 cubic decimeters. Just put my units in, my working, just show what I'm doing, and therefore you're going to get an answer of 20 grams per cubic decimeter. So nice and simple. What we're going to do now is take this equation, and I'm actually going to give you the concentration and I'm going to give you the volume, and what you're going to do is calculate the mass of substance dissolved. So I'll do one of these as a work through and then give you some more problems. So we're on B at the moment, so the next question I suppose will be C. Okay, so in this example problem, it's asking us to calculate the mass of substance dissolved in 15 cubic centimetres of a solution that has a concentration of 12 grams per cubic decimeter. So the first thing to note is that this here, I'll just change the colour of my pen quickly, this here is a volume, okay, and this over here is a concentration. Now, earlier we looked at the equation as concentration equals mass divided by volume. So therefore in this one, because we've already got the volume and we've already got the concentration, we're going to have to calculate that mass. So we can say, rearranging this equation, that mass is equal to concentration times volume. But it's important to remember though that we've still got to use everything in the correct units. So concentration, grams per decimeter cubed, is the correct units for that, and it looks like we're already in those units. But the volume, remember, needs to be in cubic decimeters if these two here are to be compatible, and the volume that we've got over here is in cubic centimeters. So the first thing I'm going to need to do is divide this number by 1000, and I will get 0.015 cubic decimeters. So now I have a volume to work with. So therefore my mass is going to be equal to our concentration, which is 12 grams per decimeter cubed, multiplied by that volume, which is 0.015 decimeters cubed, or cubic decimeters. So multiplying those two will cancel out and we'll get an answer that comes out in grams. So our mass will be equal to 0.18 grams of whatever that substance is dissolved in that particular volume. Now, why is this useful? Well, it might be that you've got an overall stock solution. So we use a flask in chemistry called a volumetric flask. So that's the world's most terrible diagram of it. It's called a volumetric flask. You've probably seen these in the lab. And let's say, for example, the volume of this thing is 1 decimeter cubed. Right, or 1 cubic decimeter. Well, if the concentration written on that bottle was 12 grams per cubic decimeter, well, that means 12 grams in every 1 cubic decimeter. So you would actually know that there are 12 grams of whatever substance dissolved in this. But if you were to actually carry out a reaction using this solution, then you're not going to use it all. You're going to take a portion of it, right? So let's say, for example, you use a measuring cylinder to take a 15 centimeter cubed portion of it. Well, you want to know how many grams are actually dissolved in that 15 centimeter cubed, so you can do follow-up calculations on reacting masses or something like that. So this is where using the concentration equation is particularly important, because it will enable you to determine a quantity dissolved in a specific amount of a known concentration, a portion of the whole as such. Now, essentially all we're doing here is multiplying the concentration by a fraction, right? Because let's say, for example, this whole volume here, 1 decimeter cubed, is 1000 centimeters cubed, right? So all we've actually done, if the concentration was 12 grams per decimeter cubed here, well, I'm saying that I took 15 centimeters cubed out of 1000 of the total. that number there is the same as 0.015. So I'm just multiplying it by the fraction of it that I took from the whole. So let's say, for example, arbitrarily, you've got a solution that has a volume, or a stock solution that has a volume of, 250 centimeters cubed. And you knew that in this 250 centimeters cubed, let's say there were 25 grams, right, dissolved in it. Well, if you took from that a small portion of that solution, let's say you took 25 centimeters cubed out, well, you would know that you've got 25 out of 250 as a portion, right? That's how much of it you've got. And you knew that there were 25 grams dissolved in the original. How many grams are going to be dissolved in this 25 centimeter cubed portion? Well, all you're really doing here is multiplying it by the fraction. So there were 25 grams in the whole, but you took this fraction, which is a tenth of it. So that's the same as saying I'm multiplying it by a tenth. A tenth of 25 is 2.5 grams. So you're just multiplying it by a fraction there. Anyway, let's move on now and give you guys some problems to have a go at. Okay then, so the first problem says what mass of solute, that means the thing that's dissolved, the substance that's dissolved is the solute, is dissolved in 20 centimeters cubed of a 15 gram per cubic decimeter solution. So you've got a volume there, you've got a concentration there. Make sure you convert your volume before doing a sum. D, what mass of solute is dissolved in 100 centimeters cubed of a 40 gram per decimeter cubed solution. So pause the video, give these a go, see how you do. Right then. So in this first one, let me just get my red pen out again. Here we go. All right, so the first thing we're going to need to do is remember that mass of whatever's dissolved is going to be equal to our concentration times our volume, where that concentration, again, needs to be in grams per cubic decimeter, and our volume needs to be in cubic decimeters. So our concentration we've got, that's 15, so I'm just going to write that in there. The mass is equal to 15 grams per cubic decimeter, multiplied by our volume. Now our volume needs converting, it's in cubic centimeters, so we're going to divide that by 1000, and you should get for that 0.02 cubic decimeters, so we're going to multiply that by 0.02. Okay, so therefore the mass of solute dissolved in that one should come out as 0.3 grams. There we go. Okay, let's have a look at our next one then. Okay then, so what mass of solute is dissolved in 100 centimeters cubed of a 40 gram per cubic decimeter solution? So mass equals concentration times volume. Again, we need this in grams per cubic decimeter, and we need our volume in cubic decimeters. Our volume is not in cubic decimeters, we're going to need to divide by 1000, and therefore we get 0.1 cubic decimeters. Concentrations in good units. So that mass will equal 40 grams per cubic decimeter times 0.1 cubic decimeters, and therefore you're going to get a mass of 4 grams. There we go, nice and simple. So now we're going to do the final rearrangement. We're going to look at how we would calculate the required volume to top something up to let's say you've got a solid and you want to make a desired concentration using a fixed mass of that solid. How much would you actually, what volume of liquid would you need to dissolve it in order to get that desired concentration? Okay then, so in this particular question we're asked what volume of liquid would 5 grams of solid need to be dissolved in order to produce a solution with a concentration of 40 grams per cubic decimeter. Well, hopefully you remember from the start that concentration is equal to mass over volume, so therefore we could say that volume is equal to mass divided by concentration. And we have a mass here and we have a concentration here. So all we're going to do is 5 divided by 40, 5 grams divided by 40 grams per cubic decimeter. And the grams will cancel out and you'll be left with an answer in cubic decimeters. Now when I did that, I got the answer of 0.125. And that answer there is in cubic decimeters. But with the measuring cylinders you're using in the lab or the glass pipettes and things like that, you're very unlikely to have one that actually measures in cubic decimeters because it's quite a large unit, a whole litre. You wouldn't measure a litre at a time. You'd want a higher resolution than that on your instruments. So you'd probably be asked for this question to actually work out your answer in cubic centimetres. So what we're going to do to convert that answer in cubic decimeters to cubic centimeters is we're going to multiply that by 1000, and then we're going to get 125 cubic centimeters, which is an amount you can probably envisage in your heads. Okay, so again, I'm going to give you a range of little problems. We're at E now, so I'll pop them up on the screen and we can give them a go. Okay then, so question E that you're going to attempt is what volume of solvent must be added, and that's in centimetres cubed by the way, must be added to 12 grams of a solid to form a solution of concentration 48 grams per cubic decimetre, and F, what volume of solvent in cubic centimetres must be added to 30 grams of solid to form a solution of concentration 0.9 grams per cubic decimetre. With your final volumes, do all the working and then convert the decimetre cubed answer to centimetres cubed at the end. Okay, give that a go for me, pause the video. Okay then, so in this first one, what we need to do with this is remember that we worked out the volume by doing mass divided by concentration. I'll just put conc there. And what we can do is have a look at the problem to see whereabouts, there we go, conc, to see whereabouts what data we've got. So we've got 12 grams and we've got a concentration over here. So I'm going to do 12 grams divided by 48 grams per cubic decimetre. Grams and grams cancel out. Our answer comes out in cubic decimetres. So the first one we get an answer of 0.25, but remember that's in cubic decimetres. So then I'm going to multiply that by 1000 and you should have got 250 centimetres cubed. Nice round answer there. All right, in the next one we're going to do the same thing. So we're going to work out that volume by doing the mass over the desired concentration. And we've got 30 grams of the solid here and we've got a concentration of 0.9. Now I think when I did that one, let's just check quickly. Let's make that look more like a 9. I got an answer, annoyingly, of 33, was it? Yeah, 33.3. Let's just check that quickly. Yeah, 33.3 recurring. So clearly there's a little bit. That's a very large number here, yeah, and it's recurring, which is quite irritating. So that's in cubic decimeters. If I multiply that by 1000, then I'm going to get 33,333 recurring centimeters cubed. So clearly 33 litres, you're going to have a bad time with that. So that's not a practical or realistic answer, but it is the answer that came out of this made up problem. Okay, so that concludes looking at concentrations in grams per cubic decimetre, which is already a skill that you should possess from your GCSE. Now what we're going to do is look at concentrations in a different format, as in moles per cubic decimetre. Okay, so now we're going to look at concentrations of solutions in moles per decimetre cubed. Okay, so this is more of what you'd be used to if you've studied triple chemistry. The concentration in this case is in moles per cubic decimetre, and because that's the units, then in order to get that concentration, what we would have done is divided moles by the volume. Okay, now typically this equation is written as C equals N over V, where N equals the number of moles and V equals the volume. And just as before, you would need to convert volumes in centimetres cubed to decimetres cubed by dividing by 1000. Okay, so let's have a look at this example question here. How many moles of sodium hydroxide are in 100 cubic centimetres of a 1.5 mole per decimetre cubed solution? So what this is really saying is that you had, let's say, a volumetric flask, again the world's worst volumetric flask, that had a volume of 1 decimetre cubed, And let's say, for example, that the concentration written on this bottle was this here, 1.5 moles per decimeter cubed. Well, again, you're not going to use the whole bottle of this. You're going to use a portion of it. And in this case, the portion of that whole bottle that we're using is 100 centimeters cubed. So in other words, you're going to pour some of that out into a beaker or a conical flask, whatever you're putting it in, and then you're going to carry out some kind of reaction using that solution there. Well, you want to know how many moles of that sodium hydroxide were there. So the equation I showed you a second ago was C equals N over V. In other words, concentration equals moles over vols. But chemists don't normally remember that equation in that format. They normally remember it in the format N equals CV. In other words, the number of moles in a given volume of a given concentration is equal to its concentration multiplied by its volume. So that's the base equation that most chemists remember, N equals CV. Most trusty equation for A-level chemistry, really, probably the most important one other than mass equals Mr. Mole. So in this particular case, we have 100 centimeters cubed here and a 1.5 mole per decimeter cubed. But remember, this volume here needs to be divided by 1000 in order to get it in decimeters cubed. So that's going to be 0.1 cubic decimeters or decimeters cubed there. And the concentration over here is great. So in order to work out the number of moles here, we're going to do N equals 1.5 moles per decimeter cubed. Let's just pop that in so we know what units we're working with, multiplied by that volume of 0.1 decimeters cubed. Okay, so that's going to cancel out and you're going to get an answer in moles, and therefore the number of moles in that 15 centimeter cubed portion is in fact 0.15 moles. There we go. Okay, so another example for you here. How many moles of sodium thiosulfate are dissolved in 20 centimeters cubed of a 0.4 mole per decimeter cubed solution? So again, we are going to use our equation N equals CV, moles equals concentration multiplied by volume. And we already have our concentration over here. We can see that because its units are moles per cubic decimeter. And we have our volume here, but we need to divide that by 1000 before we begin working on it. That will give us 0.02, there we go, cubic decimeters. So let's put our numbers in here then. N equals 0.4 moles per decimeter cubed multiplied by 0.02 decimeters cubed, and if I have calculated that correctly, you should get an answer of 0.008 moles. There we go. Okay then. Okay, so a slightly harder example now, which is going to get us to integrate two equations. So we've got here what mass of sodium hydroxide is dissolved in 50 cubic centimeters of a 2 mole per decimeter cubed solution. Okay, well, in order to work out the mass of a substance based off of concentration, then the first thing we need to do is calculate the mole. So we're going to do that much as we did before. So N equals CV, where that volume there needs dividing by 1000 to get an answer of 0.05 cubic decimeters. There we go. So we've got our volume now. So we're going to do the N equals CV to begin with. So we've got concentration of 2 moles per decimeter cubed. Let's just change that. There we go. Moles per cubic decimeter multiplied by 0.05. And I think the answer I got for that one was the moles, sorry, that's cubic decimeters. The answer I got for that one was 0.1 moles. Okay, so now I've got the number of moles, I can actually use that to work out the mass dissolved in that volume by using the mass equals Mr. Mole equation. Okay, so mass equals relative formula mass times the number of moles, and I have the moles, they're here, okay, and I'm trying to work out the mass, so clearly I'm going to need the MR. Well, I know the name of the substance, so therefore I've got to work out its formula. Well, sodium hydroxide, sodium's in group 1, so it forms an Na plus ion. Hydroxide is a compound ion, remember you need to learn those, which is OH minus. Well, that's got a plus 1 charge, hydroxide's got a minus 1 charge, so therefore the formula of sodium hydroxide is just plain old NaOH. Sodium has an AR, or relative atomic mass, of 23.0, oxygen is 16.0, and hydrogen is 1.0, so we're going to add those all up to get the MR. And that gives me an MR of 40 grams per mole. Okay, so now we have the MR. I can tick that off here. So my mass is going to equal that MR, which is 40 grams per mole, multiplied by the number of moles, which was 0.1 moles. Moles will cancel out, we'll get an answer in grams, so therefore the mass dissolved in that 50 centimetres cubed is in fact 4 grams, which is really handy, and that's actually the mass of sodium hydroxide you would get if you'd evaporated all the liquid off of that solution. So interesting use of two equations in one there. Let's have another go at one of them. Okay, so in this example here, we're asked what mass of magnesium hydroxide is dissolved in 40 cubic centimetres of a 0.8 mole per decimeter cubed solution. So we'll begin by using N equals CV, and remember that the volume needs to be converted. So we're going to divide this by 1000 to begin with, and that will give us the answer of 0.04 cubic decimeters to work with in our N equals CV equation. We've got our concentration over here because its units are moles per cubic decimeter. So therefore N equals 0.8 moles per decimeter cubed. Okay, multiplied by 0.04, and that gives me the number of moles being 0.032 moles. So I've got 0.032 moles of magnesium hydroxide in that 40 centimetre cubed sample. So now what I'm going to need to do is take this mole value across to the mass equals Mr. Mole equation, and I have the number of moles here, so that's good. I'm trying to work out the mass, but I'm going to need to work out this MR here. Well, I have a name, it's magnesium hydroxide, and I need to work out its formula in order to work out its MR. Well, magnesium is in group 2, and it's a metal, so it loses electrons, it loses 2 electrons, so magnesium is a 2+ ion. Hydroxide, however, is a compound ion that you need to remember, so it's OH with a single negative charge. Got the numbers here 2+ and 1-, so therefore I'm going to need 2 hydroxides for every 1 magnesium. Okay, just get rid of that because that looks a bit confusing there. So 2+ and 1-, so I'm going to get the formula here overall for magnesium hydroxide being Mg open brackets, because it's more than one of a compound ion, OH close brackets 2. Now what that actually means therefore is I have 1 magnesium, 2 oxygens and 2 hydrogens. So let's get their ARs and then start to assemble that MR. Well, magnesium at A level is actually 24.3, so I'll just pop that over here, 24.3 for the magnesium. Remember, I've got 2 of the oxygen, each of which is 16.0, so 2 times 16.0. Make sure you bracket this up as you go. Okay, and then we've got 2 hydrogens, each at 1.0. So obviously you'd probably write in 2 in your calculator, but hey, let's just show the full working. So we get an answer of that 4. Let me just calculate it. Okay, so our answer that we should have got for the MR for magnesium hydroxide is 58.3 grams per mole. Okay, that's great. So we've now got this MR for our equation here. So we've got mass equals 58.3 grams per mole multiplied by the number of moles, which is 0.032 moles, that should be, and there we go. We should get 1, so this is the mass, sorry, 1. Now I've got quite a precise answer here, 8656 grams. So there we go. Okay, so that's actually the mass of that magnesium hydroxide dissolved in that portion of a solution. As you can see here, what I did over here, assembling this formula, that was absolutely essential in ensuring that I got the MR correct. And it's very, very important that you use the correct formula, which is why in my earlier videos, I did actually teach you the compound ions and how to assemble formulae for ionic compounds correctly so that you get these MRs right, because actually getting the formula right means you get the MR right, and getting the MR right means you get the calculation right. So it is absolutely essential that you learn your ions and you learn the rules of how we assemble those into a correct formula. Okay, so now let's have a look a little bit more at what an A-level question would be like. Okay, so here we've got an example of an AS level question, and it would say something like this. Calculate the mass of calcium hydroxide needed to make a 250 centimetres cubed solution of concentration 0.5 moles per decimeter cubed. Now, the reason you're asked to do this is for titrations. Quite often we make our own standard solutions, which we titrate against an unknown. So we need to be certain that we have prepared a solution to titrate that is an exact concentration. So essentially what this is saying is you're going to get in the lab a volumetric flask, and that volumetric flask will have a volume of 250 centimetres cubed if you make it up to the graduated line in the neck of the flask like that. And basically what you need to do is weigh your own mass of calcium hydroxide and get that dissolved up and into that flask in order to make that standard solution. Now, the first thing we can do is we basically, it's the same as the questions we've just looked at. You need to calculate the mass of that calcium hydroxide, but in order to get mass, you need the number of moles. So we're going to do that to start with. N equals CV. Okay. The concentration we've got, it's here. Okay. We've got the volume here because that's our target volume. So that's just the same volume, but obviously that will need to be divided by 1000 in order for it to be in cubic decimeters. So we should get 0.250 cubic decimeters there. Okay, so the first thing we do is work out how many moles of calcium hydroxide that would be. So that would be 0.5 moles per decimeter cubed multiplied by our volume, which we've got because we've converted now, 0.250 cubic decimeters. Cubic decimeters cancel out, you get an answer in moles. So the number of moles we should have of that calcium hydroxide is 0.125. So now what we can do is we can take that across to the mass equals Mr. Mole equation. Okay, and we've got the number of moles, which was here, so that's good. We don't have an MR yet, so we've got to work that out in order for us to work out the mass. Okay, so we're going to need to work out that MR now. So we're given the name calcium hydroxide. I'll just write it over here to make it easier. Calcium hydroxide. So a little bit like the previous example, calcium is a 2+ ion because it's in group 2. Hydroxide is a compound ion with a single minus charge. Therefore, the formula of calcium hydroxide will be CaOH, close brackets 2. Okay, so now we need the ARs of each one of those elements in order to calculate the MR of calcium hydroxide. Okay, so at A level, calcium, a little bit more precise, we've actually got 40.1 grams per mole. Then it's got 2 of the oxygens in it because they're in the brackets, multiplied by 2 outside the brackets. So 16.0 for the oxygen, always to 1 decimal place at A level, please. Then we've got 2 for the hydrogen times 1.0. So when I do that, I get the MR for calcium hydroxide being 74.1 grams per mole. Okay, great. So we've got a MR now that we can feed into this bit here. So our mass is equal to 74.1 grams per mole multiplied by the number of moles, which we have got here as 0.125 moles. So an eighth of that. Okay, so let's work out what that mass is. And I've got a mass, I hope this is correct, of 9.2625 grams. There we go. Okay, so you've now got some practice ones for you to do. So the first one is how many moles of sodium hydrogen sulfate are dissolved in 15 centimetres cubed of a 0.1 moles per decimeter cubed solution. The second one is what mass of lithium hydroxide is dissolved in 20 centimetres cubed of a 2.0 mole per decimeter cubed solution. So you need to use 2 equations on the second one. And the third one is what mass of sodium sulfate is needed to make a 1 mole per decimeter cubed solution in 100 centimetres cubed of water. So for both 2 and 3, you need to use 2 equations, and you will also need to work out the formula of lithium hydroxide and sodium sulfate in order to do either one of those. Do pause the video now and then come back and we'll have a look at the answers. Okay, so the first one then. So we're going to need to use N equals CV to work out the number of moles. We've got a volume here that we're first going to divide by 1000, so we should get that volume being 0.015 cubic decimeters for our volume there. Okay, and our concentration is over here of 0.1. So it's going to be N equals that concentration, which is 0.1 moles per decimeter cubed, multiplied by that volume, which is 0.015 cubic decimeters. And therefore the number of moles dissolved in that came out on my calculator as 1.5 times 10 to the minus 3, so we're looking at 0.5 0.0015 moles. There we go. So there's our answer for the first one. Okay, next one then. What mass of lithium hydroxide is dissolved in 20 centimetres cubed of a 2 mole per decimetre cubed solution? So to begin with, again, I'm just going to write over here now, we're going to need to use N equals CV. We're going to divide that by 1,000 in order to use that. So our volume should be where's my pen gone? Sorry, guys. There it is. My volume, should be 0.02 cubic decimeters. Okay, so now I'm going to do N equals CV. N equals concentration, which is 2 moles per decimeter cubed, multiplied by my volume, 0.02 cubic decimeters. So the number of moles in that solution will be 0.04 moles. Okay, so we've got the moles, but we're asked for the mass. So we're going to need to use the mass equals mR times mole equation. And we've got the moles because we just calculated them, but we're going to need the mR. And we've got lithium hydroxide here. So I'll just work over here quickly. So lithium's group 1, so it's a 1+ ion. Hydroxide's -1, a compound ion. So the formula of lithium hydroxide is LiOH. Okay, so lithium on the A-level periodic table comes out at 6.9 as its AR. We've got a single oxygen, which is 16.0, and we've got a hydrogen at 1.0. So the MR of this compound is 23.9 grams per mole. So therefore, the mass will be the MR times the mole. So we've got 23.9 grams per mole, multiplied by our number of moles, which is 0.04, and therefore the mass in this one is 0.956 grams. There we go. Okay, next question then, number 3. What mass of sodium sulfate is needed to make a 1 mole per decimetre cubed solution? Okay, so in 100 centimetres cubed of water, that is. So we're going to begin by using N equals CV. This volume here gets divided by 1,000, so we get a volume of 0.1. Make that clearer, cubic decimeters. So, and our concentration here is 1. So we're going to do N equals 1.0 moles per decimetre cubed, that's our concentration, multiplied by that volume of 0.1 cubic decimeters. So 1 times 0.1 is 0.1. So our number of moles of sodium sulfate there is going to be 0.1 moles. There we go. Now this is sodium sulfate and we're asked about its mass. So next up we're going to use mass equals mR times mole. And we need to work out the MR of sodium sulfate, which means we need to know its formula. So sodium's a group 1 metal, so it forms an Na+ ion, whereas sulfate is a compound ion, SO4, but with a 2- charge. So overall, your formula for sodium sulfate should have come out as Na2SO4, 2 sodiums for every 1 sulfate. Now we need the ARs of each one of those elements in order to work out the MR. So our sodium... There it is, sorry. Our sodium is 23, but we've got 2 of them. So I'm just going to write this a little bit wide so I've got enough room. So it's going to be 2 times 23.0 for the sodium. We've got 1 sulfur in this, so that sulfur is 32.1. And we've got 4 oxygens in this, that's 4 times 16.0. Make that clearer. There we go. So our MR for this one should be 142.1, sorry, this is getting cramped now, grams per mole. There we go. So finally, we've got to do MR times the number of moles. So our mass in grams is going to equal that 142.1 grams per mole. I'm going to just not bother writing units in for the minute because I'm running out of space, times 0.1, so it's a tenth of itself. So you should have got a mass there. Oh, wrong button. It's because I'm down on the bottom of the page. We should have got a mass. It's doing it loads. There we go. Of 14.21 grams. There we go. So if you can do those, then you've pretty much mastered concentration in moles per cubic decimeter, as well as mass equals Mr. Mole. So I hope you found that video useful, and I look forward to seeing you next week for the next set of AS transition content, where we will finally start to look at titrations. Thanks very much.